The washings from procedure 2 goes into this test tube. That means there's nothing to do procedure 3. Because procedure 3 is where you do the decantate. So all you're doing is 4. Looking for mercury 1 and silver. Okay. Then you start procedure 5, which you're all familiar with. If you get a lot of precipitate here, continue. If you only get a few grains of precipitate, as you finish 5C, it says put in the casserole and boil. Okay? So when you finish 5C, you're boiling in the casserole. When you get to procedure 15, part B says boil in the casserole till you get down to 5 or 6 drops. You combine it right there. Now here you're treating with the thioacetamide, if you remember in procedure 5C. That precipitates all your group 2. When you do 15A, you're adding ammonia, then you're adding ammonium sulfide. If this is a large precipitate, you continue here, whichever one has the larger precipitate. Either you're going from 15 to 16 to 17 through that, or you're going from 6, 7, and 8 through this one. And then if you have time, you go to this one. Now if you don't get much precipitate here, and you don't get much precipitate here, you should quickly look at group 4, because that one's really easy. You're looking for barium, calcium, magnesium, sodium, and potassium. We're still not looking for ammonium. Okay? So if you don't get much here, and you don't get much here, then you want to go right to procedure 23. Because some of my unknowns most of my unknowns only have 1 or 2 groups in them. Some have something from all 4 groups. Some have traces in this group, medium amounts in this, which is more important, which is easier to find. Ones with the medium amounts. So that's the discussion of procedure 5. The only important thing again, in procedure 1, you're adding all the extra water because you want the lead to be over here in the B group. When you're doing procedure 2, if there's any precipitate. If there's no precipitate, what do I always say when somebody says there's no precipitate? Several people have said it to me, and I've said it to you. If there's no precipitate, it's all decantate. Right? The centrifuge, if there's no precipitate, it must be the decantate you're using for the next procedure where it says use the decantate. Okay, so that's experiment 5. And as I said, it's all going to be dependent on when our ammonium sulfide comes in. And for most people, you'll finish up 2 or 3. Because 3 is 45 points, experiment 5 is 50 points. 3 is easier than 5 because you don't have to do all the separate groups. So you're pushing to get to experiment 3. And people that are working on 2, tell me what you're doing right now, because if you're past procedure 6, you have things to do, because that's the only place where you need the ammonium sulfide. Okay. Except for the cadmium test, but we'll figure out something for the cadmium test when we get to it. Okay. We'll save that till ammonium sulfide arrives. So that finishes up what we want to do with the lab. Any questions? Okay. Then we're back here, we're dealing with carboxylic acids. It's the carbonyl group with the OH group on it. So this is all the whole carboxylic acid group. This is the number 1 carbon, you name the chain. This is the benzene ring, carboxylic acid functional group, special name. And we have something like this. Yes, no. Looks like a ketone, except for one thing. To have that structure, you'd have to have a double bond, single bond, two bonds, or double bond, 5 bonds at this carbon. And have 5 bonds. Then we can start putting more carbons out here with the carbonyl group and have a ketone, but we're not going to worry about that type of ketone. We could put a CHO on here, it's called benzaldehyde, but we're not going to worry about that. There's so much organic chemistry we can take, right? Or I can take. Okay, so we got to the carboxylic acids. The other thing that's functionally isomeric with that is the ester functional group. When I do esters, you see it up there? Here's ethyl alcohol. That's an alcohol reacting with an acid, ethanoic acid, and you make an ester plus water. It looks like what? Acid, base, water, salt. In organic chemistry, that's what we would say. In organic chemistry, the ester takes the place of the salt. That's all it is. Now this is an interesting reaction. This is where organic chemistry starts getting interesting. No, like I say, is that possible? Of course it is. Lots of people. There's oranges. The reason for that, the reason he has that picture, is that when you make esters, it has a very fragrant or fruity odor. Most of the things you smell in roses and fruits and things that have characteristic odors come from the esters in them. You take something like a 4-carbon alcohol and a 4-carbon or 5 or 6 carbon acid. One smells like rotten cheese and the other smells like sick goats. And you mix them together and you make Chanel number 5. Okay? That's the esterification reaction. Making esters. The interesting thing, just do this. Everybody knows acids dissociate. This hydrogen comes off. And you figure, oh, great. What I must do is making water. I'm doing that. That's not how it works. This is where we're getting to the things that are interesting in organic chemistry. It's called mechanisms of reactions. What happens is this oxygen is in the water, and this oxygen stays behind. They do this by radioactive studies. In other words, if you label this by putting radioactive oxygen in the acid, you find radioactive oxygen in the water. If you put radioactive oxygen in the alcohol, you don't find it in the water, you find it in the ester. So the actual mechanism says something strange happens here. And when you do esterification reactions, and this is, by the way, when we do the test for acetates, if we do the anions, which I don't think we will, if you do the test for acetates, it involves taking alcohol combining it with acetic acid or converting your acetate to acetic acid by using sulfuric acid, and then smelling it to see if it smells like banana oil. And if it does, you started out with the acetate. So anyhow, the OH from here combines with the H from here, and you make this thing. Now when you name the ester, oh, somebody asked me about this, about the carboxylic acid. So for the carboxylic acid, the name is formed from the longest carbon chain. Start with the carbon on the CO2H group. This is the number 1 carbon. You drop the final E, and you add OIC acid, 2 words. So this one came from ethane. This is the one I used as the example. And we drop the final E. And this one was ethanol. Now when you go to name the ester, it's made up of the alcohol part, that's the first name. You take away the ANOL, or simply the OL if it's a unsaturated alcohol, which we're probably not going to worry about, and add YL. Second part of the name, I guess I should say first part of the name because there's, well, I'll say second name, last name. You take the acid name, take away the IC acid, and add ATE. So this came from ethanol. So this is ethyl. THYL. This came from ethanoic acid. I had it written here somewhere. So you drop the IC. Ethyl ethanoate. Go ahead, I'm listening.
Yeah, in the chemical reaction, we always have to use ethanoic acid and ethanol. Can we use ethanoic acid and ethanol?
Well, you can use any acid here. What you do is you take, if you're using formic acid, it would become not form, I don't want to use, it would be formate, but let's go with the methanoic acid. Then it would be methanoate. But this is always from, the last part always is from the acid. It doesn't matter how long the chain is. It's not like the ethers where you take the longest chain as your base, the shorter chain gets the OXY. Here it always depends on the part that comes from the alcohol. This could be a 5-carbon chain alcohol, then it would be pentanyl. And the way you recognize it is you have the carbonyl carbon is the one that's going to have come from the acid. So the other one has to come from the alcohol. this thing, so it's propyl. What did I just say for this one? Benzoic acid, so it's benzoate.